Large language models are best known for generating text. But what if instead we wanted to search for text? This is where vector embeddings and semantic search come in. Instead of matching exact keywords, they use a similar training process to understand the meaning of a piece of text. This method is a smarter and more efficient way of searching for relevant data, and plays a key role in AI systems, particularly with retrieval augmented generation. A vector embedding is a numerical representation of the meaning of a piece of text. Let's build one step by step. We'll start by arranging some words along a scale from soft to hard. The result is a one-dimensional vector for each of these words, a number that represents how far along this line they are. But that's not enough. Cats and pillows are still close together. So let's add a second axis, alive and dead. Rearranging, we can see that cat separates from pillow, but if we add the word lion, that's still close to dog in our vector space. We could add another axis, like scary or friendly, to push away the lion, but how many more would we need? In practice, models use thousands of dimensions, with the small model from OpenAI using 1,536, and their large model using over 3,000 dimensions. These embeddings models are trained in a similar way to language models. They take in text as their input, process them through a transformer neural network, but instead of outputting words, they output an array of numbers in the form of a vector. This vector is what the model thinks the text means. And once in this numeric form, machines can have an understanding of the relationships between them. A nice example of this is with the vectors for king, queen, man, and woman. The difference between the vector for king and queen is the same as the difference between the vectors for man and woman. This means if we take the vector for king and subtract the vector for man, and then we add the vector for woman, we'll end up at the vector for queen. In practice, you won't just be embedding words. You can use entire sentences, documents, and sometimes even images or audio. Once you've embedded your data, you'll have a little something like this, and we can now search using it. This is done by first passing a query through the same embeddings model we used to obtain this space. Let's embed the question, what pet is good for kids? We'll obtain a vector that might end up somewhere here. We'll then calculate the distance between this and the other vectors we have. The closer the vector, the more semantically similar the content. In our case, this closest vector could be best dog breeds for families. Despite these vectors not having the same words, the space showed them as similar. That's semantic search in action. Imagine instead of this small set, we now have millions of vectors. Computing the distances one by one isn't practical. This is where vector indices come in. They're data structures built to solve a single problem. Given a query vector, quickly find its nearest neighbors. They'll use various approximate nearest neighbor or ANN algorithms, making it possible to search through millions of vectors in milliseconds. The algorithms work similarly to how you pick a restaurant. Instead of searching through every restaurant in the country, you'll start with the ones nearest to you and pick from those. A vector index is typically wrapped in a vector database, like Weaviate or Pinecone, which provide useful database features like adding, updating, and storing large amounts of data, making these indices more scalable and practical. These databases are the backbone of semantic search, enabling retrieval augmented generation, converting the generic language models into something that can harness your custom data. Instead of searching for words, embeddings now let us search for meaning.